equation 2x1 plus 3x2. Never mind. Got to back up. Sorry for the false start. I had the wrong board. Okay. This equation is equivalent to this equation. We're using x1, x2 instead of xy. Clearly, this equation has solutions. Well, solutions of white line. The homogeneous equation corresponding to this is the one that has 0 here. It has no non-zero numbers other than the numbers that are coefficients of x and y, or x1 and x2. In the homogeneous equation, s slope negative 2/3 gives you this green line. Okay, so it's kind of interesting to have these two parallel lines. They both have slope negative 3/2. Let's see how we can do this differently. Okay, we've got the equation 2x1 plus 3x2 equals 6. Same as this equation, just different names for the variables. An infinite solution set. Clearly, if we pick a number for x1, that gives us a number for x2. Pick any number for x1, we get an x2. Pick any x2, we get an x1. So either one of these variables could be what we call a free variable, a variable we can give any value to, and that determines the value of the other variable. So we have one free variable. Let x2 be the free variable, call it t. So if x2 equals t, then our equation, this equation becomes this, just replacing the x2 by t. And now we can solve it for x1. x1 is this. I'm not going to read it to you. You can watch the entire video and get that idea. So that distributing x1 has this form, so that x1, x2, well, x1 is this, that we get by solving this equation, and x2 is t because that's what we said it was. This can be split into a sum of two vectors. 3, 0, t times negative 3/2, 1. Okay, the t times negative 3/2, 1 is any number times the vector negative 3/2, 1. Here's the vector negative 3/2, 1. Here's the line defined by the terminal points of all the vectors that start at the origin that we get by multiplying t by this vector. This line then well, I've got a note here. It represents solutions of the homogeneous equation. We're not going to go there quite yet. And then we have this 3, 0. Okay. And 3, 0, of course, is one of the solutions to this equation. Okay. Any vector where x2 is negative 3/2 of x1 will be a solution to the homogeneous equation that I haven't written down. That'd be the equation where we have a 0 here. And we'll see how that works. And if we want a solution to this equation, we can take any particular solution, any solution to this equation, and add it to any solution here. And we can do that graphically. This is a vector, 3 units to the right, no units up or down. The yellow vectors. Take any point on this orange line, which is the set of these, and it moves us over to this red line. That's red with kind of pink. And this line represents all solutions of the equation. In terms of this, we see then that every solution has the form V, because every solution can be written as a vector, V equals V sub H. Now, V sub H is a solution to the homogeneous equation, where we have a 0 here instead of a 6. And again, that would be a vector along this orange line, plus any solution at all of this equation. And that would correspond to 3, 0 being one of the solutions. Takes us from this line to this line representing all possible solutions of this equation. And of course, you can verify that this line would have all the characteristics of this line, same intercepts and so forth. Okay, well, we can write the equation again, and we can also write the equation as a matrix equation. Clearly, this equation is the same as the equation row 2, 3 multiplied by the column x1, x2 gives you 6. And this equation, as we saw, has these solutions, where t can be any real number, and it has no other solutions. Well, here's a little better picture, and a little better labeled, but right here is your vector negative 3 halves 1, and same as it was before. And here is your set of solutions, okay? And goes through, you can verify, goes through the point 3, 0 and 0, 2. These, again, are your solutions of the homogeneous equation, which I've actually written out this time. 2x1 plus 3x2 equals 0, or the matrix equation 2, 3 times your x1, x2 column vector equals the 0 vector, which could also be written just 0, 0 inside of brackets. And as we said before, every solution has a form, solution to the homogeneous equation, which is one of these, plus any solution to this actual equation, 3, 0 being one such solution. Another thing that we didn't mention that I really should have thought to do because of where we're heading with this is the row space of this matrix. Okay, so the row space is the span of just the vector 2, 3. I'm writing it as a column vector because that's how we've written these other vectors. Okay, well, the vector 2, 3, well, this is 3, 0. Vector 2, 3 comes over 2 and up 3. Okay, so let's say that here's the vector, not 2/3, 2, 3. And here's the line that corresponds to all possible multiples of this vector, because of course, the span of a single vector is just a set of all its multiples. And notice how this line relates to these lines. So here's the vector 2, 3. Here's the span of 2, 3, which is this line. And when observe, haven't proven it, it's so that we have a right angle here between the span, but what between the row space and the null space. Okay, this is an important idea. So I'm going to write this down. It's a big deal, but I don't have room to write it big. The row space is perpendicular to the null space of the matrix. And of course, I just used the word null space. And I don't remember if I used it before, but the solutions of this, well, the set of vectors that map to 0 is what we call the null space. Okay, set of vectors that satisfy the homogeneous equation spans your null space, or is your null space. So here's your null space in orange, and here is your row space. And it's just going to turn out, for any matrix, the row space is orthogonal to the null space, or perpendicular to the null space. Now, if we have a system of two equations, two unknowns, we can solve it by elimination. And we get down to this equation here. Of course, we could also do this by an augmented matrix and so forth. We get down to this equation, and we see again that we're in a situation where if we specify any value for x3, we can quickly get the values for x1 and x2. Of course, if we specify a value for x1, then we get x3, and using x3, we get x2. So if we specify any one of these, we can get the other two. In the previous situation, we only had two variables. If you specify one, you can get the value of the other. Okay, just as in that case, we're going to call this a free variable. We're going to let x3 equal t and write out our solution. Okay, very simple. Put t in here, put t in here, solve for x1 and x2, and here's what you get. Then our vector x1, x2, x3, which is the vector whose coordinates satisfy both of these equations simultaneously, would be what? Well, x1 is this. So put this here where x1 is, put this here for x2, and x3 is t. So here we have this, and just as in the case of a single equation in two variables, we can write this separating out the -3, 6, 0 here, and a t times -11/8, -5/12, 1 here. Then for a different t, this form also gives us the solution. I wrote t here, wrote t here. It's a different t here than it is here. What I did is I multiplied by a common denominator here and got this vector because I didn't want to deal with fractions. So the t that we have here is 1/4 as big as the 1/24 as big as the t we have here. That's what it comes out to. Okay, so we have the solution vector expressed again as what we're going to call a particular solution, a set of numbers that does satisfy both equations. You can plug -3, 6, and 0 in for x1, x2, and x3. You're going to get an identity here, going to get an identity here. This solves the system. This is your particular solution. So this is your V sub P. And then over here, you have the a solution to the equation, the homogeneous equation. In other words, if you had zeros here and plug these numbers in for x1, x2, x3, you would get zeros. It's easy to check that. -33 times 2 is -66. -10 times 3 is -30, and -66, -30 is -96, and 4 times 24 is 96. So -96 plus 96 is equal to 0. So this is a VH, a solution to the homogeneous equation. We picture that. First, we summarize what we have. Here's the augmented matrix that represents our system. And here is the reduced augmented matrix, which leads us to this solution. And then I go to this solution just because this vector is too big to graph on the picture that I have here. It's too big compared to this vector. So I divide it by 10, and we still multiplying t by this vector, multiplying all possible real numbers t by this vector gives us the same thing that multiplying all possible real numbers t by this vector gives us. Exactly the same points, just that this t has to be 1/10 as big as this one. Okay, so here is how our solution breaks down. And again, I'm saying this fast, but you need to watch the whole 1-hour video to get all the details. Okay, here's our homogeneous system. I used an outline of a rectangular box to locate the point -3.3, -1.0, 2.4. So I could draw this vector here. Okay, or the vector we chose to represent our null space, and then the line that runs along that vector through the origin is our null space. So here is our null space. And we have our particular solution, which is -3, 6, 0, -3 this direction, 6 this direction. Here it is. We displace the vectors on this null space by these vectors, and we get our solution set. In the sense that every point on this solution set corresponds to a vector from the origin to that point, and the coordinates of that vector, x1, x2, x3 coordinates, satisfy our original equation. So that this vector or this vector or this vector satisfies the equation. Also, any vector that satisfies the equation, if applied to a point on the null space, gets you to a point on the solution set. Okay. The net result of all this, and I think I wrote this in on another board, so I'm going to look for it real quick. Apparently I didn't write it in. But anyhow, okay. You have your null space, which is the solution of this set of equations, or this matrix here without the 12, 4 here, multiplied by your x1, x2, x3 gives you the 0 vector. So that multiplying this matrix by any vector in this null space gives you the 0 vector. In a sense, you're shrinking this whole null space down to the 0 vector, and you're compressing all of space, in a sense, down to along the same line, and we'll see that later. In any case, here's your null space. Your row space consists of the span of these two vectors. And I swear that I wrote that out someplace, but I don't see it. Okay. The row space is a span of these two rows. The 2, 3, 4 vector comes out this way, over this way, up this way, so it's kind of like this. The -4, 6, -3 is -4, 6, -3, kind of goes down like this. And the plane that is defined by those two vectors turns out to be perpendicular to your null space. The rank of the matrix is 2. The rank of this matrix, I haven't written the matrix out, and it's worth writing out. So rank is 2. The nullity is the dimension of your null space. It's one dimension. It's a line. So that the rank is 2. Now, when this is reduced, it reduces down to this. Okay, so you got 2 rows that are not all zeros when you get down to the reduced echelon form. The nullity is 1 because the solutions of this matrix times x1, x2, x3 equals the 0 vector. Has dimension 1. Okay. Right there it is. This vector. So if you add the rank to the nullity 1, you get the dimension of R3, which is where this thing lives. There's more detail to what we've done up through midterm, but we started with systems of equations. We ended up with the idea of rank and nullity and all these relationships. And that's where we are now. And we really want to understand this because as we go on, it'll make life much easier if we do.